I'm going to get started. I know that some of you have questions about the quiz or the homework. We can definitely spend some time going over them. But is it okay if we finish what I have to talk about today, and then I'll save at least half an hour to go over any questions you might have about the quiz or homework. Great, thank you. So at the meantime, feel free to type any questions you might have. Just type in the chat box, or you can save it later. I'll try to go through all the questions you might have. Thank you. My week is fine, just getting a little bit busy and crowded lately. But it's almost the weekend, so look at the good side. So I hope everyone have a good week so far. At least if you haven't, try to find some time off tomorrow or tomorrow. Yeah, tomorrow the weather will be nice again, just like today. All right, thank you. Okay, so if you have any questions, just make a note of it and definitely ask them a little bit later. Okay, all right. So I'm going to get started. So this is a new material, would not be on the quiz today, but I'm pretty sure will be on the next quiz. So new material, not tonight's quiz. This will be 7.8. So we're going to skip 7.5. So 7.5, you can manage it on your own. If you're interested, it just put together different integration techniques, like good exercise problems, but we're going to not talk about that. This is the cut. 7.8 is called improper integrals. Different. Last time we were talking about improper fraction, right? So this is improper integrals. So what is an improper integral? So there are two cases. So the first type, so type 1, if the interval of integration includes infinity or is infinite, includes infinity, then the integral is improper. I'll give you an example. For example, normally let's just see, normally we integrate y equals x. I'll just take the basic example. Like we might look from a to b, where a and the b are some constants. We're looking for the area between. So we can write integrating from a to b, y, which is x, dx. Right, so this is what we call a proper integral. It's a definite integral. But if we would say we don't want just from a to b, we want going from a all the way to infinity. If we have something like this of some function f of x dx, because we have infinity as one of the boundaries, so the interval doesn't have an end, right? It is from a point and it goes continue forever. So that interval is infinite. So let me just write infinite interval. So if you have this case, then this integral, we call it improper integral. So that's the case when you have it could be the lower bound, right? Could be going from negative infinity to some number. Doesn't have to go all the way to positive infinity. So you could also have from, let's say, negative infinity to b f of x dx, where b is a constant. So that's the first case. Now the second type, 2, which is that if the function that we integrate f of x has infinite discontinuity in the interval, which is the case that, so the first case, let me redraw the diagram to reflect that. So the first case is if you have from a all the way to infinity, you're looking for the area between them, right? So that's a improper integral. The second case is that you have some function. Let's just say we're looking for the interval from a to b, but then the function between them, let's say you have a function looks like this. Right between a and the b, in the middle, you have this infinite discontinuity. The function goes to infinity or negative infinity, right? So that's an infinite discontinuity. So if we try to find the area between the a and the b, it's difficult because vertically you have a, well, the dotted line goes to infinity, right? The curve goes to infinity in the middle. How do we find the area when infinity is involved? So that's this case. So you're still integrating from a to b of f of x dx, but f of x has infinite discontinuity at some c between them. At a c with c is between a and the b. So that's the case. So the c is somewhere in the middle. You get the function goes to infinity. So when you try to integrate it, it's a little bit difficult. Okay. So let me just. Let me make it clear. At c, this could be equal. So you could have the case that we try to integrate from a to b, but the function has a vertical asymptote right at a. So this part, this part goes to infinity there, because the function has the asymptote at a. So c could be equal to a. All b. So that's the second type of improper integral. You have to look at the function, right? You wouldn't be able to tell by just looking at the interval itself. The intervals, you have to look at the function to see if it has any infinite discontinuity there. So maybe I should use a different color for f of x. Okay, so that's the two types of improper integrals that we're going to work with. Today we're only going to work on the first type. So type 1, when you have the interval, the lower bound or the upper bound or both, they have infinity. So focus on type 1. So let me first write down the definition of how to integrate them. So if we have the case, so the first one, just a few cases by type 1 definition, and then I'm going to go through some examples. Hopefully that will make more sense. The first definition says, if integrating from a to t f of x dx, f of x, yeah, that's the integral if that exists for every t greater or equal to a, then when we try to integrate from a to infinity f of x dx, we can just write it as integral from a to t for some t f of x dx, but then we have to take the limit of t goes to infinity, provided that the limit exists. To kind of boil down this part of the definition, I would say, every time you see something like this, from the interval is from a to infinity f of x dx, you just directly write it as from the integral from a to t, but adding a limit of t goes to infinity on the left side. And then you can try to integrate, and after you integrate, we take the limit. Of course, if we cannot take a limit, then we have a problem, right? We cannot find the integral. The second definition is basically the same. It's just for from negative infinity. So if integral from t to b is a constant, f of x dx exists for every t less than or equal to b, then when we integrate from negative infinity, the lower bound is negative infinity to some constant b, f of x dx, and that's going to be the same definition, which just be limit t goes to negative infinity of integral from t to b. B is the upper bound, so it's always the upper bound. But the lower bound, we replace negative infinity with t, and we add a limit t goes to negative infinity, f of x dx, provided that the limit exists. So if the limit exists, we should be able to take the limit and try to find the integral. All right, I'm almost done here. Let me add a note that I didn't include. So provide that the limit exists. When we say the limit exists in this case, we say that the limit is a finite number. So not infinity. If the limit goes to infinity or negative infinity, we don't consider that as that's valid to find the integral there. The limit is a finite value. Same thing here, the limit is finite. I'm going to write down 2 more sentences, then we should be good. So if the limit exists, we say the integral is the improper integral is convergent. That's just what it doesn't mean. That's just the sort of the condition for an improper integral to be convergent. The limit has to exist. Means that we can find a finite value for the integral. And that means we can find a finite value for the integral. Has to be finite. If we end up finding infinity, then it's not convergent. So if the limit does not exist, or the limit end up to be infinity, then integral, the improper integral, is divergent. So that's just that's something to keep in mind. If you have a question asking, oh, is this improper integral convergent or divergent? You're going to try to find the limit, see what the limit gives you. Under the third definition, which is if both from a to infinity f of x dx and from negative infinity to a f of x dx are convergent, then we can write integral from negative infinity to infinity f of x dx. We can write it as the sum of two convergent integrals, negative infinity to a f of x dx plus integral from a to infinity f of x dx. A is any number. I'm just copying this from the book. You probably all get bored of me at this point. I'm almost done. A is any number. Okay, but I'm going to stop there. But I just want to point out that all those definitions is useful when you try to find the integral. So, for example, like I said earlier, if you have an integral that going from a to positive infinity, you're going to rewrite it using the limit and the integral definition to rewrite it and then try to find the value from there. If you have the integral from negative infinity to a constant b, you're going to rewrite using this definition and then try to find the value for the integral from there. If you have something that's going from negative infinity to infinity, you're going to try to break it into two integrals, and then by picking some arbitrary a value, and then try to find the value for each one of them. All right, so those are just the definitions. Let me use examples to show you, how this works. Any questions before I start using examples? So the first example I have, which is if we're looking from 1 to infinity of 1 over x dx. This one, if you recall that the graph of 1 over x looks like this. 1 is here. Infinity is all the way at the end. So we're looking for this area. Right? That's just what that integral tells us. How do we find it? Well, the problem is that we have an infinity, so the normal definite integral technique, the fundamental theorem of calculus part 2 wouldn't work. So we have to take this and then rewrite it by using a dummy variable t. So we're going to write as from 1 to some t of 1 over x dx. But then because we use t, we have to make sure that t goes to infinity to match with the integral we have. So we add a limit, t goes to positive infinity. And then we can evaluate the integral just like we normally do with the definite integral. So that's become limit, t goes to infinity. And if we integrate this part, we get antiderivative of 1 over x is a natural log absolute value of x. Evaluate this from, I probably should have used brackets, evaluate this from 1 to t. And if you recall the graph of natural log goes like this, we only look at from 1 to t, so it's positive somewhere, right? So if it's positive, we can find the x is positive from 1 to t, we can drop the absolute value sign in the natural log. So that becomes limit t goes to infinity, natural log of t because absolute value of t and the positive t is the same. We can just drop the absolute value. Minus natural log of 1. Natural log of 1 is 0. And the natural log of t, well, let's just leave it for now. So that's equal to limit t goes to infinity, natural log of t. And then the next step is to evaluate the natural log of t as t goes to infinity. If you think about the graph of natural log, it goes like this. As t increases, the natural log goes up as well, right? Increases. So this part will approach infinity when we take the limit. So this is not a finite number, not a finite. We were able to find the limit, but the limit is not a finite number. So that means we cannot evaluate the integral. So that means the integral 1 to infinity 1 over x dx, this improper integral, is divergent. We cannot find the value for it. We cannot evaluate it. Any questions about this example and the process I did after following the definition? So all those problems, the first step is exactly, you just say it's divergent. We cannot find we cannot evaluate the integral to get a number. Or you just say, yeah, or you just say the integral is divergent. So let me just take a step back. The process is that the first step is you apply the definition, right? That's the definition we had in the book. I wrote it here, those definitions. Just rewrite it using the limit and the integral with t in it. And then the second step, you just work on the integral part. Why the extra variable? Well, we cannot, so we don't want to, this is just another, obviously you're probably saying, oh, why can't I just drop the limit and then just from 1 to infinity and then plug in infinity, right? You can't really, so you probably think at this somewhere here, you probably have like, oh, why don't I just do natural log of absolute value of x from 1 to infinity and then plug in infinity minus natural log of 1. You probably think like that. The things with infinity is not defined mathematically. We just say, oh, there's some number big, right? Really big, infinitely big. It itself is not a defined number. So you cannot take the number and plug in directly to evaluate the integral. So that's why we have to use this, this is what we call a dummy variable t. Because we can plug in some, we can say, oh, t represents some number, right? Some finite number. Then we can plug it into the natural log to evaluate it. But then because t is not finite, t actually approached infinity. So we say that t is some number. T is a variable that represents some number that goes to infinity. So t is it's a variable. It's not like it's not exactly a number that's fixed. It's a number that changes. Right? So that's why we have to use the limit there, because we cannot plug in infinity directly. But you can try to think about t represents the infinity, right? The number that goes to infinity. That's what t is. And, so the first step is apply definition. The second step is integrate. The third step is take the limit and find the limit from there. Will you lose points for not showing all steps? As long as your work is easy to follow, you're not going to lose points, right? But like I said before, it's good to show all steps as much as possible, because that's how you, if you get the final answer wrong, you will be given partial points based on the partial credit based on the steps that you're showing. And also it's good for you to check your work. All right, so that's that example. Any other questions? So the second exercise example I have is similar, but it's from 1 to infinity of 1 over x squared dx. You probably wonder if we integrate 1 over x, we get divergent, we cannot find the integral. Will this be the same? Well, let's find out. So if we follow what we did by rewriting it using the definition, because it goes to infinity, that's improper, so we're going to use a t. So limit t goes to infinity of integral 1 to t, 1 over x squared dx. I'm going to rewrite it as x to the -2. I hope you don't mind. And then this, I can integrate, so that becomes limit t goes to infinity. So the limit stays until the very end when we evaluate the limit. But the integral, I can try to find it. So that's antiderivative is negative x to the -1. And evaluate this from 1 to t. We take one more step by rewrite this as limit t goes to infinity of -1 over x. That's x to the -1. Evaluate it from 1 to t. And that becomes limit t goes to infinity. The limit still stays. Keep track of those limits in every step. And I'm just going to plug in t, so that's a -1 over t minus -1 over 1. Right, that's the definite integral. That's how we evaluate them. And the simplified, so that's a limit t goes to infinity, -1 to 1 over t plus 1. So that's all, simplifying, right? After we evaluate, that's the evaluation of the definite integral. So now we're going to plug in, we're going to pick the limit of this. So if we have t goes to infinity, the 1 over t term, 1 over infinity, that will go to 0, isn't it? It's not exactly 0, but if we take the limit, the denominator goes to infinity, the quotient goes to 0. So we just end up with just 1 as t goes to infinity, we just end up with 1. It's actually a finite number. So this number is the value for the integral that we had earlier. So this, let me use this color. So this integral, when we try to evaluate it, we end up with 1. It's not 0. Another, why is it? Oh, why is it 0? Sorry. Because if you think about 1 over t, right? If t goes to infinity, you take one unit, you divide it into infinitely many parts. Then each small part basically have nothing in it, right? That's one way to think about it. Another way to think about it is that if you have 1 over 1, that's 1. 1 over 10, that's 0.1. 1 over 100 is 0.01. As the denominator gets bigger, the value we end up with is so small, it's approaching 0. That's why we, here we talk about limits, right? Approaching 2. So this part I draw an arrow that goes to 0. That means it's approaching 0, not like equals 0. Right? So if the -1 over t goes to 0, then we just end up with 1 left. Oh, maybe I should leave it. So in this case, we actually found a finite value. That's great. So we evaluate the integral. Because it's finite value, we can also say So we can say the improper integral is convergent. If the integral, the value of the integral converges towards 1. Any questions on that? So it's sort of taking one step further from what we have done before, right? With definite integral. So now, instead of going from a to b, two constants, now we're going from a to infinity or negative infinity to b. Any questions on those? All right, as we think about your questions, I'm going to write down the next example, which is integrating from negative infinity to 0 of x e to the n. This integral doesn't have infinity, but it has a negative infinity in the interval of integration. Oh, by the way, sorry, before I move on, let me take a step back and sort of see a couple of things about the two examples we had earlier. They're so similar, right? One is 1 over x. The other one is 1 over x squared. And we evaluate from 1 to infinity for both cases. And then you probably wonder why they're different. The graph looks so similar. The area that we're looking for by using the definition of the integral, the area looks similar too. Why are they different? One gave us the actual area, which is 1. The other one gave us infinity. So this area here is 1, but this area ended up to be infinity. If you were to plot those two functions, 1 over x squared together, you will notice that this 1 over x is actually higher. So this part is higher to this one for any given x value. So the area underneath the 1 over x ends up to be sort of accumulating in a sense that it's increasing, always increasing as x increases. So the area doesn't approach to a finite number. The total area approach to infinity, just continue to increase. But the other one, the 1 over x squared, the area as you add them up to find, as x goes to infinity, the total area actually approaches to a fixed number 1. That's different. You kind of have to just, try to get your head around that. Just the way I look at it is that if you're familiar with sequence in the series, which we will talk about later, it's kind of like if you have 1/2 plus 1/4 plus 1/8 and so on, that will approach to a number 1. But if you take 1/2 plus 1/3 plus 1/4 plus so on, looks like you're adding small and small each time, that number doesn't seem to approach. I might be does it approach? I don't think that one approaches. So the second series I have doesn't approach to a fixed number. It goes to infinity if you just keep adding. So this is sort of the case that looks like this one, right? Just like a 1/2, 1/3, and 1/4, just like a 1 over x. But the first one I said, the 1/2 plus 1/4 plus 1/8 and so on. That's like the 1 over x squared case. Similar, not exactly the same. I just wanted to show you that difference. Even though we're adding smaller area each time, but the total area could still go to infinity. All right, I'm not hearing any questions, so maybe let me try to do this example with you. So this example is from negative infinity to 0 of x e to the x dx. So again, it's improper because of negative infinity to 0 is the interval. So we're going to rewrite this using the definition. So we're going to use limit at some t value, but because we go into negative infinity, so t approach to negative infinity here, the integral will be from t to 0. So t replaces the negative infinity. Everything stays the same. Exactly, that's a good point, Sam. Yes, so here when we evaluate the integral, we have to use integration by parts. Excellent. So here, let me keep the limit. T goes to negative infinity. When we evaluate this, we're going to use integration by parts. I just want to show you this example. So we can see u equals x, du. I'm going to do it quickly. You can do it in your head as well, or on paper, right? dv, I'm going to call it e to the x dx, and a v, if we integrate that, just e to the x. So integration by parts tells us that this integral will become uv, so that's x e to the x, evaluated from t to 0, minus integral of v du, that's e to the x dx, which you can integrate again, from t to 0. So that's going from limit t goes to negative infinity, x e to the x. I'm just going to write it x e to the x minus, that's from t to 0, and then e to the x is just e to the x. Again, you can just put them all together from t to 0. And the next step is plug in those boundary values. So that's the limit t goes to negative infinity of, if we put in 0 there, we get 0 times 1 minus 1, so that's a negative 1. Minus, plug in t, so that's a t e to the t. Oh, I should add parentheses. So minus t e to the t minus e to the t. So that's done integration. We have to take the limit. So let's take the limit. So that becomes limit t goes to negative infinity of negative 1 minus t e to the t plus e to the t. You have to be careful with each limit there. Limit t goes to negative infinity of negative 1 is just negative 1 minus limit t e to the t of t goes to negative infinity. You might have to do some extra work to find the limit there, plus limit t goes to negative infinity of e to the t, which you can also find. It turns out that for this problem, this part, if you think about the graph of e to the t, looks like this. As t goes to negative infinity, this term, the last term, approaches 0. On the negative infinity is here. The y value, if you x goes to the left towards negative infinity, the y value goes towards 0, right there. Under the negative 1 term, it's just negative 1, doesn't change. But what about the middle part? How do we find the limit of t e to the t? Well, the problem here is that the t will approach to negative infinity, but the e to the t will approach to 0. So this is the case, if you remember in calculus 1, you cannot find the limit directly because one part goes to negative infinity, the other part goes to 0. Which one does it approach to as you take the limit, right? So this is the part that you have to use the Locator's rule. If you remember that Locator's rule works really well when you have 0 over 0 or infinity over infinity. So what I'm going to do is I'm going to rewrite this. I'm going to just focus on the limit part. Let me use a different color. So the limit t goes to negative infinity. I'm going to rewrite it as a 0 over 0 case. So that's e to the t over 1 over t, right? E to the t divided by 1 over t. That's a e to the t times t. That's the same thing we begin with. So from here, L'Hopital's rule says we just take the derivative of the numerator, take the derivative of the denominator, and then evaluate the limit. I hope I set it up correctly. If not, we have to switch them. Oh, you know what? I feel like I'm not setting it up correctly. Let's see. Yeah, I don't like this setup. Let me switch them to t over 1 over e to the t. Can we use calc to find the limit? You should, I would say you should find the limit by, just algebraically. Don't try to use calculator. Of course, if you forget the graph of some, like an e to the t, you can look up the graph of e to the t, but you still have to find the limit. It's finding limit is important in a lot of calculus related problems. So from here, I'm going to take the derivative of t, which is 1. I'm going to take the derivative of 1 over e to the t. So that's e to the negative t. If we take the derivative, that's a negative e to the negative t. And now we can evaluate the limit. But before I do that, let me rewrite this. So that becomes 1 over negative, but you have e to the negative t in the denominator. So that's becomes e to the positive t in the numerator. Right, so that's a 1. So I probably should write negative 1 over e to the t, and then you can rewrite it as limit t goes to negative infinity of e to the t over negative 1 by flipping it around. So now if we plug in negative infinity in there, so we get e to the negative infinity over negative 1. E to the negative infinity, remember that goes to 0, so that goes to 0 over negative 1, become a 0. So the middle term also goes to 0. So we just end up with a negative 1 as the total, as the negative 1 coming just from the limit of the negative 1. The other two terms, when we take the limit as t goes to negative infinity, they go to 0. So all the work in purple that was showing to find the limit of the middle term. It just, this example, just, it just take a little bit longer when you find the limit, but the process is the same, right? So the process is still you use the definition to rewrite it, and then you integrate, take the limit. So here we found out a value, so we can always say that the integral that we want to evaluate is convergent. So the integral that we had, this one, this improper integral is convergent because we were able to find a finite value after taking limits. Any questions on this? I have one more example I'm going to go over quickly. I don't think it will take very long time. I hope you're okay with it. So the next example I have, so this will be the last one for today, and then we can do a little bit of review for the quiz. So we're integrating from negative infinity to infinity of x e to the negative x squared dx. So So here we have negative infinity to infinity, right? So what do? Well, I'm going to break it into two integrals. So that will be, I'm just going to pick the number in the middle of 0 for convenience. So I'm going to break it into integral from negative infinity to 0, x e to the negative x squared dx, plus integral from 0 to positive infinity, x e to the negative x squared dx. And for each one of them, I'm going to apply the limit definition, because each one of this is a improper integral, right? So we're going to use the limit. So the first one is a limit t going to negative infinity, integral from t to 0, x e to the negative x squared dx. The second one is limit t going to positive infinity, integral from 0 to t x e to the negative x squared dx. The integral part looks very similar. So when we find the antiderivative, we can be a little bit lazy. So let's just focus on this part. Can anyone tell me how do we find the antiderivative for this example here? U-sub, exactly. Excellent. So U-sub might be easier. You probably want to try integration by parts, but it's not easy, right? Because integration by parts, you have a problem. So here we're going to let u equals, excellent, u equals negative x squared, good. And then du equals negative 2x dx. And you can solve for dx, which is 1 over negative 2x du. Put in there. Just focus on the integral right now. So from t to 0, x e to the negative x squared becomes e to the u. Dx becomes 1 over negative 2x du. The good thing about the x is that they cancel out. So there's no x, and just negative half, you can bring it to the front. We get negative 1/2 integral t to 0, e to the u du, and then that just becomes negative 1/2 e to the u from t to 0. Those are the x values, not u. Don't get confused. So that's a negative 1/2 e to the u, which is e to the negative x squared, evaluated from t to 0 for x. So if I move on, just want to point out that this part, this is the antiderivative coming from that part should be the same for the other integral, right? So later on, we can just be a bit lazy there. Without doing all the work, we can just use it directly. But the lower and the upper bound will be different. Now let me continue to finish this problem. So now we have a limit t going to negative infinity of negative 1/2 e to the negative x squared going from t to 0. We can try to evaluate this as a limit t going to negative infinity of negative 1/2. I'm going to put in there and plug in 0, that's a 1, minus plug in t e to the negative t squared, and take the limit from there. The other side, I'm going to be a little bit lazy, so I'm going to skip all the work, and that will become plus limit t going to positive infinity of negative 1/2 e to the negative x squared. That's the same, but only from 0 to t here. That's plus limit t going to infinity of negative 1/2 times e to the negative t squared minus 0, 1. Now, if you look at each case, as t goes to negative infinity, t squared, so as t going to negative infinity, t squared is going to go to positive infinity. Same thing when t goes to infinity, t squared also goes to positive infinity, right? And then e to the negative infinity, right? E to the negative t squared becomes e to the negative infinity. That term is, you can write as 1 over e to the infinity, which is a 1 over infinity, that approach to 0. I probably shouldn't use equal, I should use arrows between them. But you sort of know what I mean there, hopefully. So that goes to 0. So that tells us that this term, this part goes to 0. This part also goes to 0. And then you take the limit of the rest, which is negative 1/2 from the first part plus positive negative half times negative 1 is a positive half. So you get 0. Wait, did I make a mistake somewhere? No mistakes. Yes, I think I'm right. So we end up with a 0. So you probably wonder, do all the work just end up with a 0? That has to do with a graph. I actually don't know what the graph of x e to the negative x squared look like, but I believe part of it is it probably looks something, because when x equals 0, we get 0. Probably looks like something like this. The left side gives you a negative area. That's exactly the same amount as the area on the right, which is positive. So when you integrate the whole thing over the x-axis, then the negative and then the positive, they balance out, give you a 0. All right, on that note, I'm going to stop here on this new material. So sorry for taking a little bit more time. Any questions on this concept? I gave you a problem set 5B. You can work on that. There's a lot of practice questions like those. If you don't have any questions on this new topic, I'm going to open up. What about 5A? 5A, we already did that. That's stuff we did yesterday, but that's not on the quiz. It's just related to 7.4. Not on the quiz, but it's related to the stuff we did earlier. So now you can work on 5A and 5B together. Not together, I think that's like a 9 and or maybe I forget how many questions in total. Maybe like 15, or maybe a little bit more. A little bit more than 15, I think, but not too many. Okay. On that note, I'm going to stop. So any questions about homework or quiz? All right, go ahead, Aiden. Okay, 21 total. Sorry, a little bit longer, a little bit more than I said. 21 problems in total.
Can I say the question to you?
Yeah, go ahead.
Okay, it's the integral of 5t minus 3 over t plus 1.
5t minus 3 over t minus 1?
dt.
dt.
Yeah.
Good question. So here, let's just look at it, right? It's a rational function. So we're probably going to use the stuff we learned more recently. Not today, but a couple of days ago, a couple of lectures ago. So if you look at it, the power of the numerator is 1. The power of the denominator is also 1, right? U-substitution can work. You can do something with U-substitution and make it work, or you can just separate it as 2 integrals. It also works. But let me use what we did lately to make it to try to make it work. So the numerator, so here degree of numerator is equal to the degree of the denominator. So it's not proper. So this is an improper fraction in the middle. So this fraction is improper. So that means we're going to use long division first. So use long division first. So whenever the degree of the numerator is greater or equal to denominator, we're going to use long division. So this is just for this case, but generally if you have greater or equal there, you're going to use long division. So 5t minus 3 divided by t minus 1. So we're going to put a 5 here because we need 5t. So put 5 there, so we get 5t minus 5. And then when we subtract, 5t minus 5t is 0. Negative 3 minus negative 5, that's a plus 5. That's a 2, right? 2 is already less than, the 2 has a degree 0, less than t. So we're not going to continue, we're going to stop there. So this 2 is a remainder. So this fraction of the integral, we can write it as 5 plus 2 over t minus 1 dt. I think it's dt, sorry. dt. So that's what we do by after we did long division, right? We get this. Now we can integrate each of them separately, which is integral of 5 dt. You can figure that out fairly easily now. Plus 2 integrating of t minus 1. I'm sorry, 1 over t minus 1.
Oh, wait, I'm sorry. The problem was t plus 1.
Oh, t plus 1 in the denominator?
Yeah, I'm sorry about that.
It shouldn't change it much. It should just only change the 2. So if you divide by t plus 1, so that's a 5t plus 5, right? And then you have negative 3 minus 5, so that's negative 8 as the remainder. So the only difference is going from 2 to a negative 8. But everything is the same.
Thank you.
Yep. And can you finish it from here on your own?
Yeah.
Okay, good. Excellent. Yeah. So always check whenever you have a rational function, always check the degree of the numerator and degree of the denominator. If the degree of the numerator is higher or equal, use long division first, and then go from there. Good question. Any other questions? Someone else? No questions? Okay, well, I guess, well, if you don't have questions, let me do a quick reminder of 7.3, because it has been a while. 7.3 has been a while. So 7.3, practice problem using trig substitution to find integrals that involving square root of either in the denominator or numerator, right? Square root of either x squared plus a squared dx. If you have this case, try to draw a right triangle called the theta. So put the x opposite from it and the a adjacent to it. And from there, you can write as tangent theta is equal to x over a. That means x we can write as a times tangent theta. So that will be the substitution for x. And if you have integral of x squared minus a squared dx, then the right triangle you draw will give you theta here. But then it's x squared minus a squared, so I'm going to call the x the hypotenuse, and the a the adjacent leg. So that means we can have cosine theta equals a over x. So secant theta is x over a. Then you can write it x equals a secant theta. And the last case is that if you have integral of square root of a squared minus x squared dx. So the right triangle we draw, that's theta. A will be the hypotenuse. It's a squared minus x squared, so a is longer than a. I'm sorry, a is longer than x. And then the x, we're going to put it as the opposite side. So there we have sine theta equals x over a, and the x equals a sine theta. I believe those are the substitution that we can use. When you work on problem like this, definitely keep the right triangles. Right? It's later on you're going to use it again at the end after you find theta, find the antiderivative in terms of theta. You're going to have to translate it back in terms of x by using the sides of the right triangle. Okay. Any questions? Any other questions? So I'm going to maybe give you a couple more minutes to think if you have any other questions. If not, I'm just going to open the quiz earlier. You can work on it. Again, just like before, you get half an hour to work on the quiz, and you have another 10 minutes to scan your work and upload it onto Canvas page. Or should I go back to what we talked about earlier, improper integrals, and go over another example? I think that'll be just more confusing to you. All right, you're ready to start. Okay, good. Okay, great, or whatever. All right. So quite a few people said, let's just take the quiz. Okay. Any objections of taking the quiz now? Like, if you feel like you still have some confusion about certain problem from the homework, you can ask it now. All right, great. Well, in that case, yep, good luck to everyone. Thank you, Daniel. Thank you. Yep, so in that case, I'm going to stop sharing the screen, and then I'm going to make the quiz available. You can start working on it.